Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver your lecture on linear algebra, chapter elementary transformations, lecture number 5, in which I will prove some theorems on elementary matrices. Before going to the theorems, I would like to remind you about elementary matrices. Let 1 0 0 0 1 0 0 0 1 be unit matrix of order 3. If we interchange any two rows, let we interchange row 1 and row 2. It is denoted by R1, R2 interchange, row 1 and row 2 interchange. Then we get a matrix 0 1 0 1 0 0 0 0 1. Elements of second row becomes elements of first row, and elements of first row becomes elements of second row, and this elementary matrix is denoted by E12. Similarly, in generalized case, Eij is said to be an elementary matrix when we interchange ith row and jth row. Second type of elementary matrix, when we multiply any row of unit matrix by a non-zero number k. Let we multiply second row by k. First row remains same, 1 0 0 0 multiply k 0, 1 multiply k, k, 0 multiply k, 0. Third row remains same, 0 0 1. And this elementary matrix is denoted by E2, second row, multiply by k. And third type of elementary matrix, if we multiply by a number with each element of a row and then add with corresponding elements of any other row. Let R3, let R3, in place of R3 we add k multiply R1, means first row remains same, second row remains same, and in the place of third row, third element of third row, 0 plus k into 1, k into 1. Here 0 plus k into 0 corresponding element, and here 1 plus k into 0, and this is equal to 1 0 0 0 1 0 k 0 0. And this type of elementary matrix is known as E3 1 multiply k, means we add with the elements of third row k multiply elements of first row, and here E12, E2k, E31k all are known as elementary matrices. In generalized form, Eij, Eik means multiplying each element of ith row of the unit matrix by k, and Eijk means we add with elements of ith row by k multiply elements of jth row, and these three types of matrices are known as elementary matrices formed by elementary row transformation. Similarly, we may get elementary column transformation, and elementary column transformation Eij remains same, Eik remains same, but Eijk becomes different. In this case, we add elements of jth column with k multiply elements of ith column. This is only the basic difference. So these are elementary matrices. We apply these elementary matrices for getting elementary transformation of any matrix, that is pre-multiplication of elementary matrix or post-multiplication of elementary matrix. Now we prove a theorem. Theorem is each elementary row transformation on M by N matrix A can be affected by pre-multiplying A by M matrix obtained from unit matrix Im by same elementary transformation. Now we prove this. Let A be a M by N size matrix. We write A. First row is A11, A12, A1n. Number of columns be n. A21, A22, A2n. A31, A32, A3n. Let here write A13, here A23, here A33, AM1, AM2, AM3, AMN. Case 1. Let we use elementary row transformation. R1, R2 means mutually interchange of row 1 and row 2. Then we get the corresponding matrix B as follow. B equal to, we write elements of row 2 in place of row 1. A21, A22, A23 dot 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 A2n, and elements of row 1 in place of row 2, A11, A12, A13 dot 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 A1n, A31, A32, A33 dot 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 A3n dot 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 AM1, AM2, AM3 dot 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 AMN. Let this is number 1. Now IM, unit matrix of order M. A unit matrix of size M by M. Here this is M by N, this is M by M. So we may multiply this unit matrix with matrix A, because here number of columns be M, here number of rows be M. So we may pre-multiply this. IM equal to 1 0 0 0 0 0 M columns, 0 1 0 0 M columns, 0 0 1 0 0 0 0 dot 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 0 0 0 0 dot 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 lastly 1. Let we use R1 R2, means interchange of first row and second row in IM. We get a matrix E12. E12 is called an elementary matrix. Therefore E12 equal to, here we write the elements of second row in place of first row and elements of first row in place of second row. So we get 0 1 0 0 0 0, here 1 0 0 0 0, here 0 0 1, third row same, other rows same, 0 0 0 dot 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 1. Now pre-multiplying E12 with matrix A, we get E12A equal to, here E12 is M by M size matrix and A is M by N size matrix. So here number of columns of E12 is equal to number of rows. So we may multiply these matrices. This A pre-multiplication E1 2. Now we multiply these two. Firstly, first row, first column of A. First column of A is A11, A21, A31, dot 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 dot. If we multiply this first row, first column, 0 multiply A11 plus 1 multiply A21 plus 0 multiply A31 and others are 0, means remains A21. A21. Then first row, second column is A12, A22, A32. So in place of A11 we write A12, here A22, here A32, means only A22. Now first row, third column is A13, A23, A33. So in place of A12 we write A13, in place of A22 we write A23, here A33. So remains A23. And similarly A2n. Now we multiply second row, first column, means 1 multiply A11, 0 multiply A21, 0 multiply A31 and so on. So here we get A11. Now second row, second column, means here A12, here A22, here A32. So only we get A12. Similarly A13 dot 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 A1n. Now third row, first column, third row, 0 multiply A11, here 0 multiply A21, here 1 multiply A31, means other 0, means we get A31. Similarly here A32, A33 dot 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 A3n, and other columns remain same, A41, A42, A43 dot 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 A4n dot 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 AM1, AM2, AM3 dot 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 AMN. This is same as B. In the first row A21, A22, A23. In the second row A11, A12, A13. In the third row A31, A32, A33 and so on. This is equal to B from 1. Therefore, pre-multiplying the elementary matrix E12 with the matrix A gives the same result by same elementary transformation performed on A, therefore case 1 proved. Case 2, let we use the elementary transformation R2. In place of R2, row 2, we multiply a non-zero number k, R2, on A, matrix A. We get a matrix C. Therefore, C equal to A11, A12, A13, A1n, A21 multiply K. K multiply A22, K multiply A23, K multiply A2n. We multiply by K to the second row. Third row remains same, A31, A32, A33, A3n, A M1, A M2, A M3, A Mn. Let this is number 2. Now we apply R2 implication K R2 on IM, means unity matrix. We get E2, second row, elementary matrix, E2K, means first row remains same, 1, 0, 0, 0. Second row 0 multiply K is 0, 0 multiply 1 is K, 0 multiply 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. This is M by M elementary matrix. Now E2K multiply A. E2K is M by M size and AB of M by N size. So number of columns of M equal to number of rows of A. So we may multiply this. So multiplication will be first row multiply first column of A. First column is A11, A21, A31 of A. So we multiply 1 multiply A11 plus 0 multiply A21 plus 0 multiply A31 and plus dot 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 dot. That means A11. Here we write A11. Then first row, second column of AB, A12, A22, A32, dot 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 dot. Here, first row, 1 multiply A12 plus 0 multiply A22 plus 0 multiply A32. Here we get only A12. Similarly, A13 dot 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 A1n. Now we multiply second row, first column. 0 multiply A11, 0. K multiply A21. K A21 plus 0 multiply A31. 0. So K A21. Now second row, second column. 0 multiply A21, 0. K multiply A22, K A22 plus 0 multiply A32, 0 and others are 0. Only remains K A22. Now second row, third column. 0 multiply A13, 0. K multiply A23. K multiply A23 plus 0 multiply A33, 0 and others are 0. Similarly, K here A2n. Now, third row, first column. 0 multiply A11, 0. 0 multiply A21, 0. 1 multiply A31. A31 and others are 0. So here A32, A33 dot 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 A3n and others rows remain same. A M1, A M2, A M3 dot 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 A Mn. This is same as C. This is equal to C from 2. Therefore, pre-multiplying the elementary matrix E2K with A gives the same result by corresponding elementary row transformation. On A. Therefore, case 2 is proved. Case 3. Let us use the elementary row transformation R1. In place of R1, R1 plus KR2 on matrix A. we get a matrix D. Therefore, D equal to, in place of R1, A11 plus K R2, row 2, A21, A12 plus K A22, A13 plus K A23, dot A1n plus K A2n. Here A21, here A22, here A23, dot A2n, A31, A32, A33, dot A3n, dot AM1, AM2, AM3, dot AMN. This is number 4. Now we apply the elementary row transformation R1 to R1 plus K R2 on unit matrix IM. We get a matrix E1 to K, means in place of first row we add the K multiply elements of second row. Therefore, E1 to K will be equal to 1 plus K multiply elements of second row unit matrix 0. Here 0 plus K multiply corresponding elements of second row be 1. 0 plus K multiply 0 and dot 0 plus K multiply 0. Second row remains same, 0, 1, 0, dot 0. Third row remains same, 0, 0, 1, dot here 0, dot 0, and other rows remain same, 0, 0, 0, dot 1. That is E1 2K equal to here 1, here K, here 0, dot 0, here 0, 1, 0, dot 0, 0, 0, 1, 0, dot 0, dot 0, 0, 0, 0, dot 1. Now E1 2K multiply A equal to, now first row of this with first column of A. First column of A be A11, A21, A31 dot 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 dot. So we multiply and get 1 multiply A11 means A11 plus K multiply A21 plus 0 multiply A31 and others are 0. Now, first row, second column, A column, second column is 1, 2, A 2, 2, A 3, 2, dot, 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 dot. First row, second column, 1 multiply A12, A12 plus K multiply A22, K multiply A22 plus 0 multiply A32 and so on, 0. And similarly, we get A1n plus K A2n. Now, second row, first column, 0 multiply A11, that is 0, plus 1 multiply A21, A21 plus 0 multiply A31, 0 plus 0 multiply A41, 0 and others are 0. Now second row, second column, 0 multiply A12, 0 plus 1 multiply A22, A22 plus 0 multiply A32, 0 and others are 0. Similarly, second row, third column, 0 multiply A13, 0, 1 multiply A23, A23 plus others are 0. And lastly, 0 multiply A1n, 0, 1 multiply A2n, A2n and others are 0. Now, third row, first column, 0 multiply A11, 0 plus 0 multiply A21, 0, 1 multiply A31, A31, 0 multiply A41 and others are 0. Similarly, A32, A33, dot 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 dot, A3n and others row will be same. A M1, A M2, A M3, dot 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 dot, A Mn. Here we see this is equal to this 4. So this is will be equal to D from 4. We have obtained D from matrix A by elementary row transformation R1, R1 plus K R2, and here elementary matrix A12K has been obtained by same elementary row transformation on IM, and here we have the pre-multiplying this elementary matrix with A. Therefore, the pre-multiplication of elementary matrix E12K with matrix A gives the same result. For elementary row transformation on A. Therefore, case 3 proved. Here it is to be noted that we have used the elementary row transformation in a particular row by taking particular rows. So we may take here in place of R1, Ri, here Ri, here K, Rj, and we may generalize this. So we may get the generalized result in each case. Hence, we get that pre-multiplication of the corresponding elementary matrix with the given matrix gives the same result for the elementary row transformation of the given matrix. And our theorem is proved. In a similar way, we may use the elementary column transformation, and in that case we have to post multiply of the elementary matrix, and we will get the same result. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button. And if you have not yet subscribed my YouTube channel, then please subscribe my YouTube channel. Thank you.